Hello everyone. During this 15-minute session, we wish to share with you our experience from the Australian continent. The topic for this session is Learning from Australia, Area-Wide Apparatus License Methodology in the 26-28 GHz band. My name is Yaya. I'm a senior spectrum engineer for the past 10 years with ATDI. I'm based in Sydney and I will be the speaker for this session today. I will also stay for the QA in case there's any questions. Alright, this session is only 15 minutes long, so I kept the outline to the minimal. First, we shall define AWL license type, talk about its main highlights and features. Then I will be discussing the methodology to manage interference in AWLs and take the modeling to simulation environment, tools such as HTZ Communications, to demonstrate practical use cases on how to compute the AWL area. For this exercise, I will be taking the FSS Earth Station transmitter as an application or as a use case for the AWL license, where the technology needs to coexist with other band users such as the millimetric wave 5G. So the AWL stands for Area-Wide Apparatus License, recently introduced by the Australian regulator ACMA as a forward compatible, flexible and technology independent license type. It came as a response to evolution in the technologies and industry demands in general. This new licensing framework can be applied to several bands, each with different technical constraints. It is an area approach and based on grids. It is both flexible and scalable. In AWL, the licensee is licensed to operate in the limits of allocated and gridded geographical boundaries. The new license type has several advantages. For example, it can be utilized for a range of network sizes. So we're talking about 1 to 10 transmitters or maybe 100 transmitters. The same license applies to all these scenarios. It's technology neutral, so we're not talking about 5G, we're not talking about FSS or others. So it's a technology neutral. So like sharing one band between 5G and FSS satellite uplink, for example, they're both on the 28 GHz band in Australia. Also, another advantage is the ability to license as a transmitter or receive only. So you could define the license for reception only or transmission only or both. And that's obviously providing protection if you are using this for reception. Okay, for example, if you're doing downlink reception. Main features. Now let's talk a little bit about the features of this license. So as it is obvious by now, the license is area based, not location based. So we're not talking about actual coordinates of a site. We're talking about the boundary, the area of multiple sites. So there is a predefined geographical boundary or a fence made of aggregated grids or cells. The licensee is required to adhere to the technical constraints within this license boundary. The interference to other services is managed through the boundary constraints itself, not individual devices used in that license area. So you don't have to be concerned about device-to-device interference. It's more like area-to-area interference as a whole. Because of this area concept, it is possible to take a neutral technology approach. Same license methodology can be applied to multiple technologies. The license area can be small or can be large. or can start small. Okay, you can have a couple of devices with a small boundary, and later on grow over time. Okay, to expand. Can support a variety of technologies and also frequency bandwidth combinations. Individual AWLs can also be aggregated to form a larger AWL license, as you can see on the right hand side. So here on the right hand side you see there's two areas, two AWLs. Each one of them is made of many smaller grids. So this is the first boundary here on the left, and then the second boundary. So you could actually join these two and then work with the overall license boundary. Managing interference. When it comes to interference and coordination, the interference is managed from a very high level, and that is primarily to simplify the process. Interference is treated as area to area and not apparatus to apparatus. So the right technical constraints for the boundary itself must be clearly defined. This is usually established using a concept such as the PFD limit, for example. So you can put a PFD limit, and then we use the PFD limit to establish the footprint of that network. So area representation has also been simplified by defining a nationwide hierarchical grid, as you can see in the bottom right corner over here. So you can see we've got a very high level grids, and then each grid has more granular detail, has more smaller grids. So there's multiple grid levels involved. These grids are available in multiple levels to address the needs of small and large license areas and license boundaries. The license, taxes, and registration process are achieved by defining the cells. So you need to have the cells, each one of these grid, being requested for licensing. HCIS, or Hierarchical Cell Identification Scheme, used to define the geographical area of the license and avoid overlaps. This allows license area to be accurately mapped to the area in which a licensee is planning to operate, and to minimize arbitrary boundaries, the boundaries that can potentially lead to inefficient use of spectrum. So like small spillages and so on. So any whatever spillages that are there, everything is managed or captured in these cells, in these grids. Technical guidelines are provided by the regulator to assist in establishing the license boundary for a given application. These technical guidelines are typically closely followed by registered private assigners. So in Australia, we have private assigners. We call them accredited persons, or APs, who go through the proper modeling and analysis to establish HCIS cells that require licensing. So these are this is like the regulator is relying on the private sector, on the industry itself. These are private frequency assigners that can do the analysis and following the framework set by the regulator. So they adhere to these conditions and these guidelines, and then they identify the boundaries that need to be licensed for a given applicant. Now let us see a real example to better understand the modeling requirements for the establishment of AWL boundary for the case of FSS Earth Station transmitters on the 28 GHz band. In this case study, we have a NGSO, non-geostationary orbit Earth Station transmitting on the 28 GHz band, which is also shared with millimeter wave 5G network in the country and in that band. The tool used for this use case is HTZ Communications from HDI. So we're going to use that tool to demonstrate how this AWL license boundary is established in the tool. There is also a webinar on this topic, a very long webinar. So this is the example we have in front of us. There's a millimetric wave considerations on the 28 gigahertz, and we also have the fixed satellite services. Like we said, the NGSO is going to operate in this band as well. So they have to share the band with the 5G millimetric wave. So the use case here I have is someone applying for uplink license for the Earth station, which is connected to NGSO. So we need to establish the footprint of the license. So to do this kind of modeling, you need to have a certain modeling capabilities. So here we're using the digital terrain model from the software. And we're also using digital clutter model, and these digital clutter models are available in multiple resolutions. So this is describing the RF environment. So these two pieces of information are critical for proper modeling and simulations. So here we're using satellite image to see where we are, and here we have the model for the Earth station, which is operating uplink for NGSO on the 27.9 gigahertz, as you can see here. These are the parameters, technical parameters. So we define transmission power per megahertz, antenna gain, frequency, antenna height, and we have the antenna pattern following ITU, and we've got the tilt or the azimuth information, but obviously there will be tracking involved here. So this is here what we're doing. Here the simulation is based on an Earth station transmitter with variable elevation and azimuth orientation, because like we said, it's NGSO. So the tool is going to vary the antenna orientation and compute the emissions for all possible combinations. Finally, cut off the emissions following the PFD limits, as you can see here. So these PFD limits will be applied to the footprint, and then based on the footprint we could establish the license boundary required. So this is a practical use case and realistic as well. So you can see on the right hand side we're doing computation from 350 degrees to 10 degrees. Okay, and then we're doing elevation for 10 degrees. You can do it from 0 to 10 degrees or 10 degrees to 80 degrees and so on. So you can specify the range. And then you do the computation, and then the software will produce the footprint of this emissions for all possible combinations or orientations. So after that, you can see here the tool is going to import. The tool can import the grid over Australia. These are the grids. So you can overlay the coverage that we produce of the emissions boundary and the grids, and then the tool will identify which grids are actually overlapping with the emissions, with the emission limit, and then it's going to list for you the cell ID or the grid ID. So you can see here in the comment, it's a polygon. So JV3N9Q, JV3N9U. So these are the unique IDs assigned by the regulator to each of these grids. So this is a unique way to represent the grid. So we could identify the overlap between, and the tool is doing this automatically, as you can see here in the bottom left corner. The tool is identifying the grids that are overlapping with the coverage. So you know you have to pay the license for 1, 2, 3, 4 grids. Sometimes it's more, depending. So this is the topic we wanted to discuss in the 15 minutes. If you have any questions, you feel free to ask later on during this event. And this is also our contact information. Thank you.